Hello, folks. Dr. Paul Piquel here. I'm an assistant professor of teaching at the University of British Columbia in the Faculty of Forestry. And in this video, I want to show a demo of using the Mind Test game to visualize real worlds. And to achieve this, I'm using a program or script that I've written that is called gis2minetest. And this program essentially takes real world geographic data and converts it into these blocks that essentially get assembled into a Minetest world. So if you've ever played or heard of Minecraft, Minetest is simply an open source version of that game. To show you what this looks like, let's jump into it. I'm going to start a game up here. And this is a location in Malcolm Knapp Research Forest, and this is located just outside of Vancouver. So this is actually a cut block in that forest, and you can see that we have some nicely differentiated trees here, good amount of slope coming down on this cut block, and then some other forest on the other side of the cut block. And yeah, this is a great example, I think, of using a point cloud to create, sort of real world experiences so that you can literally jump right into this, what would really be a LiDAR point cloud, but in this way it's much more interactive. And also, everything is sort of true to scale. So these blocks are 1 meter by 1 meter, and the heights of things around you are true to their scale. The only thing that I had to sort of play around with was creating the actual tree stems in this case. So everything else is coming from LiDAR except for these tree stems. And if I took away the tree stems, then essentially the LiDAR point cloud would look kind of weird because you would just see a bunch of canopies of trees just sort of floating around in space, and that didn't look very realistic in my opinion. So I wrote an algorithm that essentially applies a focal maximum function to the canopy values and essentially finds the highest canopy points within a specified distance to other canopy points, and then writes out the position for that location, and then I just repeat a block pattern of pine trees all the way down in this case. So that's how these stems are created. So these stems are not actually coming from LiDAR. They're not detected by LiDAR whatsoever. They are basically artificially or let's say programmatically created. Nonetheless, it does create for a more realistic forest, in my opinion. And that's to say that it looks nice, but these aren't the actual locations or the number or the density of the actual tree stems. We don't really know those. The other thing is that you can actually walk into these forests. So I'm flying around, but I can also walk in here. And the cool thing about Minetest as a game engine is that it provides shader, which is basically a function of the game engine that produces all the illumination effects as well as the atmospheric effects. And so this actually makes it really useful for looking at lighting patterns, for example, within forests. And it's a great way, I think, to teach about light interactions underneath the canopy forest, as well as just outside of the forest and sort of edge effects that can happen there as well. So yeah, that's very cool. The terrain here is also derived from LiDAR. So if I kind of zoom back a little bit, and you can kind of get a good appreciation for the scale of this slope. It's quite gradual, but it does extend over a large area, and so yeah, this terrain is derived from the LiDAR point cloud, and then we just build all the stuff that's on top of it, and we classify each of these block types based on what the classification of the LiDAR point cloud is at that location. So yeah, this is all very cool. This is, I think, a great example of a real world that you can visualize and simulate. Even in this cut block, these are some slash piles, I believe, that were left behind. These little vegetation areas down here. And yeah, you can kind of explore this world on your own terms, which I think is really cool. You can change the time of day and experience different shading or shadowing effects and all kinds of cool stuff. Of course, the nice thing in Minetest, just like Minecraft, is that you can also build stuff. So in creative mode, you have access to a whole library of all kinds of different materials if you want, and I can go up to any one of these trees and just start destroying it. So that's it's kind of cool that you can also create your own world. You can modify things quite quickly and see what the result might look like. So that's all fun and cool. I want to show some other examples of using the digital terrain model and showing some derivatives from that and how we might be able to visualize some different GIS data. So this is, again, the Malcolm Knapp Research Forest, the same location. I've just removed the trees. We're only looking at the terrain here. And what we're actually looking at is the slope of the terrain, and it's classified into, I think, 5 or 6 different classes, and those are colored based on the intensity of the degree of slope. And for most places, the slope is quite gradual throughout this whole area, from 1 meter to 1 meter. And there's a few places, I think, up here that have slightly higher slopes or slopes that are approaching 60, 70, 80 degrees, indicated here by these red blocks. But for the most part, it's a pretty gradually sloping area, no matter where you look. But nonetheless, you can actually turn on the overhead map. It gives you a bird's eye view up in that right-hand corner. And that's what this slope map might look like if you loaded it into ArcGIS or QGIS, a two-dimensional representation. So, really being able to dive into the data, I think, is a really cool aspect of this technology. You can really get a better understanding of, if you were a student, of how slope is actually being calculated. Because you can go and investigate it for yourself and see how these values are being encoded into that raster grid. But more importantly, I think, even if you were just doing your own sort of data exploration, you can really get a much better appreciation for these fine topographical features, like this little gully that seems to come through here, that you can't really see very well through two-dimensional maps. And this is, maybe if I zoom or fly all the way up top, oh, now I'm in the clouds, that you can kind of appreciate what the difference is between being from that perspective all the way down to the actual ground itself. So that's slope. I also have an example showing aspect. So aspect is the cardinal direction of the slope. So again, the same area in Malcolm Knapp Research Forest. I'll kind of fly around, let it load up a little bit. And the aspect here is encoded in 8 different directions. So you have red, for example, that is facing north. And the other cool thing about this Minetest game engine is that there is a sun. So that sun, as you can see, it's slowly rising as the clouds are also moving. And so the cardinal directions in these maps are also true and correct. So you can see here that these red pixels, for example, or these red blocks, are encoded because they are encoded red because they are facing northward, and that would be east, and that's south, and that's west, and then there's also the intermediate directions like southeast and northwest and so forth. So you can really see, again, if I put on that bird's eye view, you can see what this would look like if it were a two-dimensional map. I think in the upper right-hand corner is kind of an example of what you would be seeing if you were loading this map in 2 dimensions. And yeah, it is really cool to be able to go in here and explore. And again, if you're a student, to have a better appreciation for how these calculations are happening and what it actually means. Like to actually go in and blow up a pixel to a real-life scale. And just kind of see how the data are being encoded, I think gives you a better appreciation for what you're actually looking at in your final product. And as well, it brings up interesting questions. It's like, why are these flat areas all colored gray? And that obviously has to do with the slope calculation because there's no change in the slope. So there is basically a zero aspect there, or an undefined aspect there. So that's aspect. And I have a couple more examples. This one's interestingly showing a hillshade. And by the way, these are all calculated within the program using GDAL, which is a geospatial data abstraction library that's open source that provides the functionality to calculate slope and aspect and hillshade and things like that. So this is hillshade, which is kind of a funny one to visualize, I think. It's also a bit challenging to visualize in minetest because there's only four gray levels to actually work with. There's black, white, and then two intermediate gray values. So this is really only a, I guess it would be a two-bit image of hillshade. But presumably you could add a mod or a texture pack that actually provides a full 8-bit color depth or gray levels leading from 0 to 255, and you can kind of visualize this a little bit better. But even the overhead visual there kind of gives you an idea of what the hillshade looks like, and yeah, again, you can fly in here and kind of better understand how this hillshade is being calculated based on the actual terrain that you can experience and walk around in. The last one that I wanted to show is the topographic position index, and this is just another example of a calculation or derivative that you can get from a digital terrain model. And again, this is color coded based on the intensity of this topographic position index. So topographic position index is essentially a calculation of how different or how rugged the any given pixel or location is relative to the 8 neighbors. And for the most part, this is a pretty flat area that's very gently sloping. So there's not a lot of variation in this, but you can again kind of see how different pixels and different locations are mapped or colored in different ways based on their values. And like for all these blue pixels, you can see most of them are they have quite a bit of variation around them. And yeah, so that's an example of the topographic position index, which is pretty cool as well. So that's all for now. Thanks for watching.